My name is Tian Xu, and I'm presenting practical urban localization for mobile AR. This work was done during an internship program at ByteDance last summer, and I would like to thank my mentor Guohui Wang and my advisor at Purdue ECE, Felix Lin, for their valuable input. Places of interest AR applications are emerging. Those applications could be widely applicable to urban areas where the merchants proliferate. And the AR effects are specific to the exact camera location and position. And the AR effects are interactively and continuously rendered in real time. The POI AR could open a new door to deliver relevant advertisements. For instance, while a user points her camera to a coffee shop, the smartphone renders the coffee promotions as a virtual overlay on the screen. The POI AR effects can be diverse and is compatible with all the existing AR types, like marker-based, markerless, and superimposition. For marker-based, the AR effects are overlaid on known physical objects such as a QR code, and the AR effects will be anchored to that position. For markerless, the AR effects are rendered in real space, in free space. For example, when the user wants to purchase a new type of furniture, she can compare the different choices by placing a virtual 3D furniture in her living room. For superimposition, AR effects provides an alternative view of an object. For example, a virtual overlay aligned on the building wall. POI AR needs twofold location information. The first is the POI label describing the user's current location. And the second information is the 6 degrees of freedom camera pose, which is composed by the camera position and the orientation. The current localization solutions are inadequate. For GPS, the devices can be blind in urban street canyons because the signals transmitted through the device and the satellites can be blocked by the tall buildings, so that the localization error can be up to 20 meters. More recently, Wi-Fi-based localization reduces the error to decimeter level. However, it only provides the 3 DOF location and is limited to indoor environments. So computer vision is a more robust alternative. So these slides show a typical workflow of the computer vision solution customized for localization. On the left-hand side, it describes the ahead-of-time construction. So people will collect a collection of image data and extract the image features from those data to construct a geovisual database, which correlates the geolocation with the image features. At the runtime, when the user points her camera to a building, the camera images will have the relevant features extracted and compared to the features pre-extracted in the geovisual database to find the most similar image. And then they can get the POI information. Through the others computer vision algorithms, it can continuously infer the 6 DOF camera positions to support the real-time AR rendering. So 3D reconstruction is a commonly used and a commercial solution. During ahead of time, people will collect 2,000 images per building and extract the features from all those images, and it takes another 4 hours to generate a 3D point cloud. At runtime, the features from the camera images will be extracted to infer the POI location, and the 6 DOF camera positioning will be derived by the perspective endpoints algorithm to support the real-time AR rendering. The advantage of this approach is its high accuracy. It can reach centimeter level error. However, it often includes colossal volume of data collection and expensive 3D point cloud generation. Although it has been adopted by industry like Scape Technology and Google Visual Positioning System, in some cities, but it's not scalable to the large urban area. So above solutions are either inadequate or impractical. For GPS, it suffers from its own high error, and it can only provide 3 DOF positions. For Wi-Fi, it's limited to its indoor environments, and it can only infer 3 DOF position. For 3D reconstruction, the major drawback of this approach is the huge cost during the ahead-of-time construction. So to this end, we present a practical localization pipeline for POI AR with 2 cheaper and complementary CV algorithms that could work in tandem to compose the entire workflow of computer vision localization. These 2 algorithms are image feature matching, which is a low-cost POI recognition technique, and simultaneous localization and mapping, which is a real-time 6 DOF positioning technique. And compared to the prior solutions, our proposed solution can work in both indoor and outdoor environments with low error, and it can also provide 6 DOF position in real time with the low ahead-of-time construction cost and the low runtime cost. So for feature matching, it's a low-cost place recognition technique, and it covers the workflow of the image data collection, image feature extraction, and the vocabulary tree construction. So the vocabulary tree is a very classic data structure that defines a hierarchical quantization of the features that is built by hierarchical k-means clustering. So during the runtime, for the features extracted from the camera images, it will search in this vocabulary tree to find the most similar features to infer the POI. So with the POI label recognized, SLAM can provide the 6 DOF camera position in real time to support the AR rendering. SLAM is widely used in localization in unknown environments, and it is already the base of some common AR development toolkits like ARKit or ARCore. So to design such a system, we have a few challenges. The first one is the high search overhead in a large vocabulary tree, because the search latency grows monotonically with the number of features. So if we only cover a few buildings, things could be fine and we can infer the POI in a very short time. However, if we want to scale to the entire urban area, there could be hundreds of thousands of images. So to search the similar features in that large tree, the search latency could suffer. The second challenge is the potential privacy leakage, because in prior work, people usually upload their camera image to the cloud and run the image feature matching on the cloud. However, this includes the sensitive data transmission between the device and the cloud, and it could be vulnerable to some side channel attacks, or the attackers can utilize the malicious Wi-Fi to review the user-sensitive information. The third challenge is the proportional cost to different AR types and real-world environments. So our first major design is a low-cost construction with vocabulary forest. So we first collect tens of images per building that usually cover the multiple positions and orientation of that building. The next step, we will detect the irrelevant entities, for example, the human or the automobiles or the trees that happens to be included in the image collected, and we will remove those visual features from the irrelevant entities by detecting the bounding boxes of those irrelevant entities through some generic object detectors like YOLO. And in the third step, we will index the visual features as a vocabulary forest, which is composed by multiple shallow trees that cover the entire area instead of the monolithic tree. The benefit of doing this is that the search latency will drop monotonically with the smaller tree coverages. So for the entire region, we will first segment this region into segment the entire region into a few subregions. For example, region A to region G, and for each region, we will construct its own vocabulary tree and store them on the cloud database. The second design is the incremental tree prefetch. So at runtime, the device prefetches the vocabulary tree corresponding to the region that the user is about to enter from the cloud. Doing so avoids the severe privacy leakage because it avoids uploading the user camera image to the cloud. And there are a few optimizations. We prioritize the tree prefetch based on the overlapped region size between the GPS arrow range and the nearby tree coverage. So the GPS arrow range could be a circle with a radius of 20 meters, which is the typical arrow of GPS signals. And in this case, the largest overlapped region is with region A. So we will prioritize to prefetch the vocabulary tree that cover region A first. The second optimization is predicting the user trajectory from crowdsourced digital footprints. So on some popular social websites, the users tend to upload their AR effects so that we can study from the crowdsourced digital footprints to predict the most popular places of interest and prioritize to prefetch the vocabulary tree that cover that popular place of interest. And third one is the adaptive tree placement, because keep downloading the tree will stress the device storage. So we will replace the pre-downloaded trees based on the least recently used policy. Third design is the adaptive 6DOF camera positioning to have the proportional cost to different AR types and real-world environments. For example, for marker-based AR effects, the tolerance of localization error is much larger because if you want to tag the building name, you just need to place the AR effects on that building wall, which is normally a few meters. And the per frame delay is tolerable to approximate 1 second because it does not need an interactive and continuous rendering of the AR effects. For markerless that renders an AR object in a free space, the localization error is typically considered to be less than 1 meter, and the delay should reach the real-time requirement. And for superimposition, because it provides an alternative view of the object, the tolerance error is smaller than 10 centimeters, and it's a very interactive AR effect. So the delay should be tens of milliseconds, which should also be rendered in real time. So the system should also adapt to various real-world environments. So for some buildings, they have distinct surfaces with insufficient features to extract. So in this case, we will raise the resolution or sampling rate to enhance the accuracy of the localization algorithms. And if we have a high camera moving speed, we will raise the number of features to detect so that the correspondence of the feature points between two frames can be more accurate. So we did some preliminary experiments. So the vocabulary forest construction is much cheaper than 3D reconstruction. So we estimate a case for Palo Alto, a medium-sized city in California. So the vocabulary forest requires 100K images. However, the 3D reconstruction will require 10 million images, and our approach can save approximately 100x. And for the generation time, the vocabulary forest is only 12 seconds per building. However, the 3D point cloud requires 4 hours, so we save 1.2kx. And for the storage cost, we also save 20x because we avoid storing the RGBD voxels, and we only need to store the feature vectors. And smaller trees are faster and more accurate. So we collected the images, 10 images per store from 11 stores on University Avenue in Palo Alto, and we used the DBOW2 for our vocabulary tree library. So the x-axis represents the number of stores covered, and the y-axis on the left-hand side is the search latency, normalized to 1 on 4 stores. And the right-hand side, the y-axis represents the accuracy. So we can see the trend that with more stores covered, the search latency will go up. And from 4 stores to 11 stores, the latency will go up 50%. And with more stores covered, the false positive rate will also be higher, and the accuracy will drop from 92% to 80%. So in conclusion, we propose a practical urban localization solution that supports the POI air, which significantly reduces the ahead-of-time construction cost, alleviates the privacy concerns, reduces the online user wait time, and adaptive to various AR types and real-world events. So for future works, we will expand to larger image dataset and prototyping the tree prefets in the real world with proposed trajectory prediction, and design a demo AR application to stress test the adaptivity of our system. Thank you.